Hello and welcome to this EE228 lecture on viewing Fourier series from the perspective of linear vector spaces. Or said another way, how can we view this topic in 228 with the eyes of someone who just took a linear algebra course? So as a review, one of the major topics in a linear algebra course is the notion that any vector in a space can be written as the linear combination of other vectors in the space. So on this slide, I just want to remind you that we can talk about the vector x, maybe as the ordered pair 1, 2. And if you want to write x as the sum of two what we call unit vectors or basis vectors, maybe u1 and u2, then the default way to think about this is the first element of the x vector is the multiplier on the first unit basis vector, and the second element in the x vector is the multiplier or scalar on the second unit basis vector. So in this way, if we're just talking about what's called the standard basis, we can find out the scaling factors because they are encoded directly in the vector x. However, for any given vector space, there are many possible bases. So in the last slide, we talked about the unit vector u1 and u2. For a number of reasons. They're called the standard basis. They are easily represented on two axes. And they have some other beneficial properties. In particular, they are what are called unit vectors, so they have unit length. So we say the norm of u1 and the norm of u2 are both 1. And also, in fact, most importantly, they span R2. And that means that you can get anywhere in R2 by taking linear combinations of these two vectors. But they are not the only two vectors that span R2. In particular, down here, v1 and v2 also span R2. So they don't have the nice feature of being unit vectors, and they also don't lie on the common axes. But sure enough, if we look at v1, the vector v1, and the vector v2, if you were to take scalar multiples of v1 and v2 and add them to each other, tip to tail, you could get anywhere in the plane. Okay, so v1 and v2 also span the space. And so the relevant question, I think, is if we don't have a quote-unquote nice basis, how can we express any vector x in the space as a linear combination of v1 and v2? How do we get the scaling factors? And so the answer that you learned in your linear algebra class is this notion of projection. And so to project x onto a vector, say v1, means to ask ourselves how much of x, when, say, a light is shown in this direction, how long is the shadow of x onto v1? And in this case, the shadow is actually longer than v1. But I hope what you see here is that this vector, from the origin out here, is going to be some scaled version of v1, where we don't quite know the scaling factor yet, but because it's in the direction of v1, it's going to be a scaled version of v1. So for now, I'm just going to call that scaling factor p1. And we could do the same operation down here. We could now shine a light in this direction, and then the shadow cast by x onto v2 would be this vector. And so this is in the direction of v2, so this vector, I think it would make sense to call some scaling factor p2 times the vector v2. And so if I were to add this vector to this vector, I would get to this point here, which we're calling x. And so one of the big results in your linear algebra class was this notion of projection and how to make this mathematically rigorous. And so the idea was that you learned that the projection of any vector, x, say, onto another vector, v1, say, can be gotten through the dot product, also called the inner product. That's not quite true in general because we also then have to divide by the norm of v1 squared. But this operation, this is called a projection operation, tells us the amount of v1 contained in x. And so note that this is going to be a scalar quantity, right? A dot product gives us a scalar, and a length squared gives us a scalar, so the division here is going to be a scalar quantity. And likewise for P2. This is the amount of x in V2, and then normalized by the length of V2 squared. Okay, so if we have P1 and P2, then it's easy to write any point in the plane x as P1 amount of V1 and P2 amount of V2. And we have formulas for P1 and P2. Okay, that's all well and good. This has been a review of your linear algebra class. What comes next is a little bit mind-bending. And so it's this point that I want to make, and that is there's nothing that makes us talk about tuples, and tuples are just a fancy word for these kind of things, 1, 2, 3, J, 5. So these are tuples. These are ordered lists of numbers. And they are commonly what you may have learned about in your linear algebra class. So this is an element of the space R3. This might be an element of the space C2. And that's fine because there are notions of addition for these vectors, and there are notions of scalar multiplication for these vectors. But my point on this slide is that any collection of stuff or any collection of things can be a linear vector space if it obeys these two simple rules. So these are the only two rules in order to call a collection of things a vector space. And the first one is if you pick a thing from that collection and you scale it by, say, a real number, then the resulting thing has to also be in the collection. Okay, so this works in R2 because if you take any vector in R2 and you scale it by any number, real number, sorry, you will get another vector in R2. Okay, so we say that linear vector spaces are closed under scalar multiplication. And then the second rule is that the two things, if you add any two things from the space or from the collection, you are guaranteed to get another thing in the collection. And again, to remind you why this works, pick any two vectors in R2. If you add them together, you get another vector in R2. Okay, there's no way to leave R2 by adding two vectors. But the point of this slide is that this generalizes to all things for which addition is well defined and scalar multiplication is well defined. And so just the general math term for these things is a vector. A vector doesn't have to be an ordered pair or an ordered triple or whatever. A vector is anything that obeys these rules. Okay, so in particular, I would like to ask you to consider the fact that functions can be vectors. So what do I mean by that? Let's be a little careful here. So let's talk about only functions that are, say, periodic. And so let's consider only functions that are periodic with period big T. And so what would have to happen if these functions with period T were in a vector space or were vectors? Well, these two rules would have to apply. So pick your favorite periodic function, and I'm just going to sketch it over one period. I don't know. So maybe your favorite function looks something like this, or not. Literally any periodic function, sketch it between 0 and big T, and then scale that function. Well, for my favorite function here, this is going to be something that looks like this, which is also going to be periodic with period T. Okay, so these functions are closed under scalar multiplication. Now, pick your second favorite function defined on 0 to T. I don't know, mine might look something like this with a discontinuity. So if I were to add the triangular shaped function with this step type function, I hope you would see that I would get another function that is periodic. So the idea here is we might have something that looks like this, and then something that looks like this, but it would then repeat itself. It would again go down to here and go up to here. So by adding periodic functions, I get periodic functions. And so I think we have just checked both of the boxes to show that functions defined on the interval 0 to t, which are equivalent to functions that are periodic with period big T, are closed under scalar multiplication and addition. So therefore, they form a vector space. The next question I'd like to address is, what would a basis for this vector space look like? Or, said another way, what would a linear combination of these basis vectors have to look like? So far, all of your vector spaces that you've considered in your introductory linear algebra class have been finite dimensional. So these were the examples, R3, C2, and these indicate the dimension of the vector space. Another way to think about the dimension of a vector space is the smallest number of vectors you could use to span the space. Okay. In the space of periodic functions that I just described, you have what's called an infinite dimensional vector space. So there are an infinite number of basis vectors, but remember, vectors and functions, when I'm talking about vectors now, I'm talking about functions. So really, these basis vectors might be better described as phi 0 of t, phi sub negative 1 of t, phi 1 of t, etc., etc. And if I've got an infinite number of basis vectors, then taking a linear combination of those basis vectors would look like an infinite sum. And that's what I've got down here. So remember, these are basis vectors, aka basis functions. And these x sub k's are scalars. Or you can think of them as scaling factors. They tell us how much of each basis function do we need to get to the original function that we're talking about, the original vector that we're talking about. And so the main question that I hope you're asking is, how do we get these scaling factors? The answer is actually the reason why we did the introductory part of this lecture, and that is you just have to project. So the answer is we need to project x, which is our vector, onto each basis vector. Now, there's an infinite number of these, so we need to have some kind of pattern to follow. But the answer to this question, how to get the scaling factors in this linear combination, is the exact same as the answer how to get the scaling factors for the linear combination of, say, R2 vectors. Now, I've just kicked the can down the road because now the question is, how do you project one function onto another? For R2 case, it was kind of easy. You had this idea that you could shine a light and you could figure out the length of the shadow. I hope it doesn't surprise you that that concept kind of falls apart when we talk about functions, projecting functions onto another. But at the very heart of it, in order to project one function onto another, you need an inner product, right? That was the heart of the projection in R2. Right, the projection of x onto v1, remember, was x dot v1 over the size of v1 squared. And so this notion, this dot product, is the key. And what we call a dot product in an infinite dimensional vector space is simply an inner product. So if you think about inner product and dot product, I'd like you to think of them as synonyms. So how do you dot or take the inner product of two functions? Well, that needs to be defined. And so the definition that I'd like you to use for the inner product of two functions on the vector space of periodic functions with period t is this. We're going to divide by the period length. We're going to integrate over one period of the first function times the complex conjugate of the second function. Okay, so what might this look like in practice? Let's look at an example. So let's take f of t is the complex exponential e to the jt. And in this case, g of t, let's take its complex conjugate. So the two functions that I'd like to take the inner product between are e to the jt and e to the minus jt. Okay, so you would write this as f of t inner product with g of t. So we need to work out the period of these functions. So what does the graph of these functions look like? Well, if we plot it on the complex plane, we can look at the real and imaginary parts of the function. And if t is 0, then we have 1. And as t gets bigger, we spin around the unit circle. So my claim is that both of these are periodic, and they are both periodic with period 2 pi. Because once little t gets to be 2 pi, both of these functions, one of them spinning that way, and the other is spinning that way, both of these functions, it's the same direction. Both of these functions are periodic. F spins counterclockwise, G spins clockwise, but they both get back to 1 after 2 pi seconds. So this allows us to divide by 2 pi, integrate from 0 to 2 pi. The first function, e to the jt, times, and this is important, the conjugate of the second function. So the second function was e to the minus jt. If the complex conjugate of that is e to the positive jt, dt. So I want to run that by you one more time. G of t is e to the minus jt. The conjugate of g, so g star in our case, is e to the minus jt. So that's where I get this plus sign. Okay, so let's combine these exponentials. That'll make our integral a little bit easier. Integrate from 0 to 2 pi of e to the 2jt dt. Take the antiderivative here. We get 1 on 2j. And then evaluate this from 2 pi, which gives us 4 pi j, minus e to the 0, which is called 1. So one more trick that I want to show you is that if I go around 4 pi radians, then again I'm on the unit circle. So here's 2 pi radians. If I go around 4 pi radians, I get back to the point 1 on the complex plane. So my argument is that this is also 1. And so the inner product of f with g, we just showed, is 0. And that's okay. Lots of vectors will have inner products that are 0. The important bit is that I showed you that taking the inner product between two functions gives us a scalar. Just like taking the dot product between two tuples gave you a scalar. Okay. So the reason that this notion, these angle bracket notations, are called an inner product, which is the analogous, which is the infinite dimension analogy of a dot product, is that lots of the things that you associate with dot products are also associatable with this inner product. That is, orthogonality is a big one. If you take the dot product between two tuples and you get 0, that meant that they were perpendicular. Well, in higher dimensions, we call perpendicular things orthogonal. And so the function x of t and y of t are orthogonal if and only if their inner product works out to be 0. So using our example before, this means that e to the jt and e to the minus jt are orthogonal functions. Now this is important to realize that we're no longer talking about perpendicular things, primarily because both of these look like very similar functions. They both look like circles. Here's e to the jt, and here's e to the minus jt. Right? There's nothing perpendicular about these two graphs, but from a functional sense, from a functional analysis sense, these two functions are orthogonal because their inner product is 0. And the way to think about this orthogonality is you can go ahead and generalize perpendicularity, because if two vectors were perpendicular, then there was no projection of one onto the other, or the shadow cast by this vector onto this vector had 0 length. So the higher dimensional analogy here is the shadow cast by this function onto this function is nil. And the other big concept that grows from finite dimensional vector spaces to infinite dimensional vector spaces is this notion of size, or norm. And that is the norm of a vector in a linear vector space is still the square root of the inner product of that vector with itself. Okay, so this is also sometimes commonly written with the square on the other side. And so in our inner product space, this would be divided by the period length, integrate from 0 to t of the first function, x of t, times the conjugate of the second function. Okay. And so was one more thing I want to show you, that this x times x star, well, what do you get when you take a number and you multiply it by its complex conjugate? I hope you remember that that gives you the complex magnitude squared. Okay, so I only bring this up because you've actually seen this integral before. This is the formula for the power of a periodic signal. And so what the particularly nice feature about this inner product definition is that the size of a vector is its power. Okay. And I hope that makes sense, that bigger, quote-unquote, bigger functions, periodic functions anyway, have more power, and vice versa. Also, it's impossible to have negative power, just like you can't have a negative vector length. Okay, so to wrap this up, we have proposed to us from Mr. Fourier that this set of vectors, so this is called the exponential Fourier basis set, that is the set of exponential functions whose frequency is an integer multiple of the fundamental frequency, form a basis. This is a set, this is an infinite set, because k runs from negative infinity to infinity on the integers. That's important. Integers only. This is an infinite set of basis functions, and the claim is that if this function is what's called a Dirichlet function, that is, it satisfies the Dirichlet conditions, then you can write this function, also known as a vector, as a linear combination of basis vectors. So this is a linear combo of basis vectors. Right? This is, say, x sub 0 amount of e to the 0. It's x sub 1 of e to the j 2 pi on big T times t, etc., etc., etc. It's an infinite sum, but it is a linear combination of basis vectors. And then how do you get these x sub k's? How do you get these scaling factors? Well, the answer is project. These x sub k's represent the projection factors of the original vector x of t onto each of the basis vectors e to the jk 2 pi on big T times t. And so the formula for projection is exactly the same as it was for finite dimensions. You take the inner product. Remember before this was a dot product, but we're generalizing that. The projection is the inner product of the vector onto the basis vector divided by the norm of the basis vector squared. Okay, so if you scroll back to the beginning of the video, that's the exact same phrase I used, but replace inner product with dot product. And for this particular set of basis vectors, and for this particular definition of inner product, this always reduces to the following integral. And so these are actually familiar to you at this point. These are known as the Fourier series synthesis equation and the Fourier series analysis equations. And I say plural there because there are an infinite number of these equations, one for every integer k. So there you have it, the exponential Fourier series described as the outcome of a linear algebra exercise. Thank you everyone for watching, and I'll see you next time.